Okay, so now to construct an econometric model, you need to, what we call it, you need to go through these 8 stages, or there are 8 steps for you to do in order to construct an econometric model. So the first step is to state the hypothesis. You need to have to come up with a statement of hypothesis. What we call that, how you expect the relationship between the dependent and independent variables. And then the second step is to specify the mathematical model, specification of mathematical model, and then a specification of econometric model. So just now I already explained to you what the difference between mathematical and econometric model. And then collect data or analyze data. And then the next one is to estimation of econometric model and interpret regression result. And then the step number 6 to specify, to perform the specification testing and then diagnostic checking. This one basically on the specification testing, whether we use the correct model or not, and then diagnostic checking on the residuals. Okay, because we need to specify a number of what we call the assumption to make sure that the model is a valid model. And then test of hypothesis, and the last one is prediction. So this is what we call that flow chart for econometric modeling. So first you need to refer to the economic theory and then state your hypothesis. Okay, if you don't have, if there is no available theory suggesting relationship between that particular y and x, then you need to state your own what we call that hypothesis on how you expect the relationship between y and x. Okay, and then you what you call that specify the mathematical model and then econometric model, and then get the data, and then what we call that inspect the data. Okay, and then after that you perform estimation and perform the specification testing and diagnostic checking on the residuals. And then if the model pass all these tests, then we say the model is an adequate model, and then you can perform hypothesis testing on the model, on the predicted or estimated model, and then you can use the model for forecasting, or we call it prediction, to do prediction. If not, if the model fail any of the tests, then we say the model is not adequate model, it's not an adequate model, then you need to reconsider the model and find or try to specify the alternative model, and then what we call that redo all this procedure. So if you consider an example, let's say student performance at university level. So we would like to construct or to build an econometric model to explain what we call that the relationship between student performance at university level and the factors that determines the performance. Okay, so there are a number of possible determinants of the student performance. So including the ability, student ability, family background, and effort by the student itself, for example, to do revision. When, just before they have exam, for example. However, for this example, we just consider simple regression model. So meaning that we only have one. So in this case, let us look at the ability only and make analysis based on a bivariate model. So we call as a 2 variable, or we call as simple regression. So for the stage 1, the first step, what you need to do, state the hypothesis. So let's say we say the function of student performance is given by a student performance determined by his or her ability. So we consider only one factor, explanatory variable. So the next step, you need to specify the mathematical model. Let's say we decide to use linear equation, linear model, and then so which is given by this now. So you state the performance P is a function of dependent, or it is depends on ability. So P is a function of ability. So in linear form, you write down the equation like this. So y equal to n intercept plus beta 1 x. Okay, so if we assume that this equation will give exact value to y, this is what we call as a mathematical model. So in the mathematical model, what we have here is exactly the same value to this one. But again, as I mentioned before, so in this case, Y is the performance, X is the ability. So as I mentioned before, in econometric modeling, most of the time we won't get exact value. So this one, when we make prediction, the equation won't give exactly the same to the true value of the response variable. So in this case, in that case, we need to have an error term. We need to add error term plus the error term so that we call it as an econometric model, no longer mathematical model. So this mathematical model where the value of the right hand side of the equation is exactly the same to this one. But I mean, most of the time we won't be able to get that prediction exactly to the same value to the actual value, so that we need to add an error term. Although it's possible, sometimes it's possible for certain value of X, it's possible to get the same value for this equation and the Y, but most of the time we won't be able to get exact value, so that we need to have an error term. So in this is Y represent performance, which is the dependent variable, X the ability in our independent variable, and Y and the U is a disturbance terms or the error term. So for the true value of what we call that the true error term, we call as disturbance terms, but when we estimate from a sample, then we call the error term as a residual. So we use different terms. So for this example, we will collect data. So we need to collect data of average grade at pre-university level and cumulative grade point average at university level. So let's say, so you collect your data. So let's say in this case, the ability, you use the performance at pre-university level as a proxy for the student ability. So what I need to do, collect data, and then so collect data. So in this case, our dependent variable Y, so observation for Y, GPA at university level, and the X, the average grade at pre-U level, and then perform explanatory data analysis using both descriptive statistic as well as graphical inspection. Okay, so descriptive statistic, numerical, the numerical analysis, you inspect, for example, you inspect the minimum, maximum value of the each of the variable, and then the variance, standard deviation, and so on. And then you also I mean, it is good that you inspect the graph of the CD as well to identify or to get the initial idea how the relationship between Y and X. So the graphical chart like scatter plot give us early identification of possible error, the isolated data points and outliers. So I mean, if you identify based on the scatter plot, if there is what we call the extreme value or outliers that you feel that it will make your estimate to be incorrect, then you should take out that one. You should take out the extreme value first before you estimate the model. So let's say this is the graph for the given example. Okay, so we have CGPA at university level, and then average grade at pre-U level. So you produce scatter plot. This is what we call scatter plot. So you have Y and X. So you can see that. So what can we observe regarding relationship of the CGPA at university level and average grade at pre-university studies? So in this case, you can only make subjective assessment, okay, by looking at the graph. So you can see that it seems that there is positive relationship between the student performance at university level and the ability, which is in this case we use the previous performance of the student at pre-U level. So based on the graph, you can see that as the value of X increase, the value of Y, the dependent variable, also increase. So it seems that they have positive relationship. So this is what we call a subjective assessment. So just based on graphical inspection, but it does not tell us what we call the exact the magnitude of relationship between Y and X. So in order to know by how much, when for example, the previous performance, the CGPA at pre-U level increased by 1 unit, how much it will influence the value of CPA at university level. So you need to estimate in order to find out the answer. So estimation of parameters, the next step, y and x are variables, which is known. So the two variables we can see, y and x, it is known, but beta 0 and beta 1 are parameters. So which is, I mean, it is unknown. We do not know the true value. So, and u is also unknown, as it depends on beta 0 and beta 1. So in our equation before, so this is y and x are known. We can see the values. The data we have y and x, we collect the data, so we can see the value. So it is, each of these is known, but the value, the true value, the true relationship between the two variables, beta 0 and beta 1, as well as the error term, the true error term, are unknown. We do not know. So we need to estimate this as well as the error. Okay, so the method that we're going to use to estimate is a method known as ordinary least square, or OLS estimator. So OLS regression line is the line that minimizes the residual sum of square for the data point. So we would like to estimate the intercept, because in this case, let's say we decided to use, we feel that linear equation is the best, what we call the representation of a relationship between y and x. So in this case, so we need to estimate this. So because linear, so basically it is a straight line linear equation. It is straight line. So you look at its graph, there are many straight lines you can draw to represent relationship between the y and x. The straight line will give you the intercept, the one that the value, what we call the value of y, where the line intercept, what we call the intercepting this, the y axis, and then what we call that the line also gives us the slope of the line that represent, the slope represent the estimate of beta 1. So basically there are many lines you can draw. So there are many possible lines you can draw to represent relationship between y and x, but in this case, which one is the best one? Okay, so so we use ordinary least square means that we would like to find a line that gives us the smallest sum squared of error. So just now I already explained to you the error represent the deviation, I mean the difference between the actual value. So this is the blue, each of these dot represent the true value of y, and then the value on the straight line represent our predicted value. So the difference between the actual y and the predicted value, the systematic behavior, so give us the error. So we would like, so in this case, in order to find or in order to determine the best line, so we need to find a line that gives us the smallest sum squared of error, the sum squared of error. Okay, so the method on really square regression line is the line that minimizes the residual sum of squares for the data points. So in this case, we find a line that minimizes the sum squared of error. We do not want the line that minimize the sum squared, or minimize the sum of the error, because the error can be positive, negative, because if the actual value higher than the actual value, the predicted value, then the error is positive. But if, for example, this one actual smaller value than the predicted value, so the error is negative. So if you simply take the average of the error, sum of the error, then it's possible that the positive, the positive error will cancel out negative. So we don't want that kind of situation, because, for example, if you consider two situations, let's say you only have two observations. The first error is positive 2, and second error is negative 2. If you take the, what we call that, the sum of the two errors, it is equal to 0. So it gives us impression just like there is no error, but there are errors. So you cannot take, taking a sum of error is not what we call a good idea, in order to find the best line to represent the relationship between the two variables. So instead, we should take the sum squared of residual